Hello everyone, I'm Wei Tan. Today we are going to introduce the concept of laminate stiffness and strength. This again is a very important concept in the mechanics of composite material. Let's firstly define what is laminate. A laminate is two or more lamina bonded together to act as integral structural elements. What is the classic lamination series? Basically, we have assumed a few things. Firstly, the plies are perfectly bonded together. The bonds are infinitely small, thin, and do not distort in shear. Therefore, the displacements are continuous across laminar boundaries. As you can see here, if we have a bilayer structures under 3-point bending condition, we will have a continuous displacement across the boundaries. Therefore, even the two layers has different properties, we assume they will deform at the same time with a smooth displacement. In that case, of course, their stress will be different. And secondly, we assume that the normal to the middle surface remains straight and the normal to the middle surface after bending. For example, at the beginning, the straight beam, you have a straight line, okay? Basically normal to perpendicular to your middle surface. And after you bend the sample, this straight line will still perpendicular to the middle surface, the neutral plane. Okay, this is our assumptions, and we assume the strength through the thickness is negligible, where the epsilon z is almost zero. Based on that, we can try to derive our equations. Also note that the shear strength gamma xz and gamma yz equal to 0 in this case. Firstly, we need to use the classic strain displacement relation. As you can see, we just start with two layers. If you have a two-layer structures and you bend these two-layer structures, what will happen? Let's just track a few points, A, B, C, D. Once you bend it, A, B, C, D prime are all still on the same line. But the question is, you want to ask is, what is the deformation of the beam? Particularly at a certain point, for example, at the point of B. The point B essentially is the middle point of the top layers. After deformation, you have the B prime, right? So in that case, what will happen here? We want to find out, originally you have UB, okay? And let's find out the equations. And UB essentially is the distance from the B point to the B prime point in the horizontal directions. And U0 in this case is essentially we are looking at the neutral plane, the C point before and after the bending. And what is the main difference here is actually adding a very small amount of deformation here, okay? And here we need to use the angle here, where we assume after bending you have a small angle difference. This is called alpha x. And alpha x here essentially is the same as the angle here. So here I have a zoom in figure like this one. So that can help us to work out the relationship. Imagine that the alpha x is this angle, so tangent alpha x will be equal to the small amount of change x divided by the side length zb, which is zb. So we can work it out as x equal to zb times tangent of x, and assume this is a small angle tangent of x will equal to alpha x. So we will have x now equal to zb times alpha x. Alright, and in that case now we have our relationship u0 equal to ub plus x essentially plus zb alpha x. We can rearrange the equation. Now we get this one, ub equal to u0 minus alpha x zb. And similarly in the other direction, vb will be equal to vb minus alpha y times zb. Okay, now the question is how we are going to use these equations. vb is essentially the vertical direction. I will leave to you to derive these equations. Now I just wanted to find out how we can use that. For arbitrary bending deformation, you can imagine the ub can be any place. Although u0 doesn't change, but ub can change to any place. So that's ub can be replaced by u here in the general conditions. And the angle here now is basically alpha x essentially is equal to delta w divided by delta x. Okay, delta w is the changing of your in the vertical displacement, and alpha y is delta w over delta y. Okay, and use that equation, you can simply further derive their strain relationship, because we will have actually the definition strain essentially is equal to delta u over delta x for the sigma y, and epsilon y essentially is the delta u of delta v over delta y. And basically you essentially do a derivative of your u against x. That's how you get this equation. And similarly, do a derivative of against y, where you have these equations. And for the gamma xy essentially is delta u over delta y plus delta v over delta x, and you will get another equations. Okay, lastly, we just need to denote some of this double derivative with the curvature value kappa x and kappa y. This is the curvature. Okay, and kappa xy is the shear curvatures. Now let's move on to see how we can use these equations. Consider a laminate under the membrane and the bending load in the x directions as shown here. And you can think about the strain of the materials can at any point is equal to firstly the strain at the neutral plane, okay, epsilon x0, plus the actual, caused by the bending. So one of them is z. Z is the distance between your arbitrary point to this neutral plane z. And the kappa x is basically the curvatures. It's a double derivative of your vertical displacement. Right, that's essentially the simple form for your equation. Okay, now we can write them including both epsilon x, epsilon y, and gamma xy. And where you can see that this is the middle plane strains plus the curvatures, right? And with that, that's our basically starting point we need to always remember. Use the stress strain equations for laminar we have learned in part 3. We know sigma x y is equal to the reduced stiffness tensor times the epsilon xy. Now the stress in laminar J means any laminar here, is given by sigma xyj times this certain stiffness matrix times the epsilon xy. Now epsilon xy can be expressed by these equations we have derived. Okay, and if you want to know more about this relationship, like the stress in a laminate, you can see sigma x, sigma y, tau s. You can expand that stiffness matrix by these equations at a certain layer. Before we call J here K, essentially the same things here. And then we basically substituting the expressions for the strains. We know the strain, as you can see, strain is equal to epsilon 0 plus z times the kappa, as we shown here, right? And we expand our matrix to this one, and as you can imagine, sigma xyk now is equal to the expanded form. Okay, and now let's move on. Recall we have this stiffness matrix component can be expressed by the Q11 and the M and N. Okay, this is transformation matrix component. In general, the reduced stiffness matrix will be different for each laminar. In that case, then the stress distribution through the thickness of the laminar will be discontinuous. You can see the strain is continuous as it's like follow our assumptions. But our effective stiffness is a zigzag pattern. Therefore, our stress will also have zigzag patterns. Okay, essentially strain times stiffness will give you the stress. Now let's look at a simple equilibrium conditions. For example, this is the bilayer structures. We just look at actually a single layer structure. Even a single layer has a middle plane. In that middle plane, we want to look at a unit width like the width of that part is 1, and the very small height delta z. Okay, and in such case, what you're looking at is the force. We know basically the relation is force equal to the stress times area. And in such case, because we know we're just choosing unit width, right? Then what we are getting is we just need to use area is basically the width times the height, right? And now we have the stress term sigma x, and we have the basically width equal to 1 times the height. In this case, is a small height delta z. Okay, we can write that in the integration form such that over the whole volume here, you can go through an integration from negative half t to positive half t, which essentially the bond here, and times the sigma x and dz. Okay, that's essentially the force per unit width. And similarly for the moment essentially is the force. Okay, moment is the force times the distance, the arm length, right? So essentially on top of that you have the extra term, the distance z, which is the one here, and that gives the moment. And now we have both of them, force per unit width and moment per unit width, and in the integration form. Essentially what you're doing is you have a different differentiation element or small element. Now you can integrate all these small element across the beams. Okay, that's how you do it. And now we have done something together for each directions. We have just shown an example in x direction. You can do not only x direction, you can do that in y, in s, and you can also derive that moment, the moment against x axis, moment against y, the moment against s. The only thing you need to be aware, s means actually the shear directions. Okay, the shear direction within the plane, the shear direction within the plane is like this. Now we need to find out the equilibrium conditions for all the laminates. You can imagine those many layers stacked up across the thickness. The stress in each laminar can be integrated over the thickness of the laminate to give the middle plane force resultant N and the middle plane moment resultant M. That's all we need. Okay, we are looking at this middle plane. I'm using a dashed line to highlight this middle plane. All our calculations have this as a reference, and we're trying to add them up. Okay, before we only have this for one layer. Now you can see we have a sigma from the first layer 1 to the layer n. Okay, you're basically adding up all the layer, and this gives you the total resultant force N. And similarly, this is the total resultant moments. We can expand this form, okay? If you remember what we have done before, the strength equal to the strain at the middle plane plus kappa times z, right? And all of them can be actually expanded in different direction, x and y, z. That's why now you can see this term in x and y and z, x, y, and shared directions. And now you understand this term and this term as well. We can further, you can imagine, this is just one layer. We have this. And what about the total force for the laminate? This is the laminate. So now we have the extra term to add all of them together, okay, from one layer to layer n. And we always have this integration term, and we always have this strain term. Basically, you just from here, and you consider the accumulated effect from many layers. When you expand it, you will get the results showing here, and you will have, as I can see, a few terms here, nxy, okay, and if you can simplify the equation, it becomes like determined by the a and b xy, epsilon z, and kappa. You know, essentially all of them is a condensed form, okay, condensed form. This form can be expanded to one here, and this form can be expanded to here. The reason for this actually is you can imagine that just simply do an integration against z, dz. Okay, that will give you half z squared, and from the upper bound zk over the lower bound zk minus 1. Okay, so that is the dk and dk minus 1. So essentially, when you expand it, it will give you the term here. Right. And similarly for the moments, you essentially expand them from here to here, from here to here. And we can simplify the from term with A, the second term with B. Similarly here is B and D, right? Because these two terms is the same. We therefore can have the full pictures when you actually writing out the total force resultant, nx, mx, and then you have all the matrix lined up. A11 is the subcomponent of the A matrix, and the B have a subcomponent for the B matrix, and D similarly here, and you can write them in a condensed form, right? Now we can actually look at individual term here. A can be write as sigma all of them together, and as you can imagine, this term essentially is the laminar thickness of each layers. And in that case, you can try to do something here. If you have 0.45 and minus 45 symmetric, and what will happen? Essentially, for A matrix, if you just swap the layout 45 degree, 0, 45, symmetric, it won't change the A. Okay, A is independent of laminar sequence. Whatever you put there, the A will be still the same, because unless you change the laminar thickness, otherwise it's the same. Let's look at B and D. Now B, you have this term dk squared minus dk minus 1 squared. And here is the cubic, it's even different. And B and D are both functional laminar sequence. And this is the reason, because if you put the layer difference, like 0, 45, minus 45, slightly difference, these two terms will be changed. Yep. The reason for that is, if you go back to a few slides back here, when we talk about the definition of zk minus 1, they are the distance from your layer height, okay, from your layer height to your middle plane. Understood? So essentially, it's no longer simply like just the distance here. You have a non-linear relationship. The laminar thickness and laminar sequence will be changed if you substitute your values in. Okay? And this is so-called laminate coupling effect, where A13, A23, some of the term B11, B12, B22, and B13, B23, they are all causing different type of deformation of your laminar. Right? For example, D13 and D23, if they are not zero, they will cause some like flex out of plane. A13 and A23, if they are not the zero, then you'll cause some shear deformations. Now let's look at the physical meaning here. A13 and A23 couple the shear strain to the direct stress, the shear stress to the direct strain. Right. Eliminate this coupling if you make them A13, A23 equal to 0 by using a balanced laminate. What that means is, whenever you have a positive angle laminar, you will have a negative angle to balance out. For example, 45, and then you have minus 45. In that case, you will always get A13 and A23 equal to 0. For B is coupling the bending behavior to the membrane behaviors. So, for example, you have a high modulus on the top, low modulus in the bottom, and what will happen is, if you eliminate the coupling B equal to 0 by using a symmetric laminate, you wouldn't have this issue. B will equal to 0, like we're showing here. In this case, it's unsymmetric. Okay. Or non-symmetric. But if you put something in between, and this at the middle layer and this is symmetric, this will lead to B equal to 0. As long as you submit your value there into our equation B expressions, where you the K, ZK and ZK minus 1, you will find if you put a symmetric layers, this will be equal to 0. Okay, and D couples bending and twisting behaviors. The bending and twisting behaviors, we go back, which essentially this is the twisting behaviors. You want to eliminate something to get D13 and D23 equal to 0. And here I'm showing some example. Symmetric layers, essentially you have a S here showing is symmetric. Anti-symmetric is like this. And you have a 0, but you have a negative 0. Sigma 2, you have a negative sigma 2. Instead of have just a sigma 1, sigma 2 to sigma 2 over sigma 1. That is symmetric. And this unsymmetric, now you see, is actually unsymmetric. Sigma 1 is not matching any of these things here. Okay, this will generate different value of ABD matrix, and therefore it will introduce different influence like twisting effect. If you look at the source of bending twist coupling, okay, you will get something like this because the D matrix is actually changing. It's not 0. Right. To eliminate this coupling, if you try to substitute value, you will find you want to use an anti-symmetric laminate. Okay. This is particularly useful in some of the scenarios where typically have a bending and a twisting happening. You don't want that happen for that, for example, wind turbine blade. So normal strategy is to choose a balanced and symmetric laminate, and choose so that actually you want to position the positive laminar as close as possible to the negative angle laminar to minimize the bending twist coupling. For balanced symmetric laminate, the constitutive equation now become something more simpler. Okay, you can cancel some of the term out, and the B essentially just equal to 0. Alright, as you can see, we can also use a parallel axis formula for ABD, just like we use that for calculate second moment area. And A essentially is sum of the A prime of each layer, adding them together. And B now has a slight different equations. I'll just show the equation here. We can have some extra lecture to explain why there's this expression here. Let's look at an example just to illustrate what we mean. And for this sub-laminate 1, we can see you will have the layout 0, 45, 40, negative 45, 90, 90, negative 45, 45, 0. This is essentially a symmetric layout and also balance. Therefore, you will have the certain values equal to 0. For sub-laminate 2, again, very similar. For the full laminates, now you can use that parallel axis theorem. You can use A equal to 2 times A1, the B equal to B1 plus B2 minus the term here, and D13 equal to D3 equal to 0. Now it's anti-symmetrics because you have a 45 degree, now you have negative 45. You have a negative 45, now you have 45, 90, corresponding to 90. So in such case, actually, you're getting a quite good layout is balanced, is symmetric, but also is in such case, or in this case, is also give you the minimum bending, twisting, coupling. Okay, in this case, this value equal to 0, but actually is somehow. Let me go back to that slide so we can see the definition of, yeah, this is so-called anti-symmetric. It's still different with unsymmetric. Okay, this is not the thing we want. Anti-symmetric. Right. Therefore, a laminate with no coupling effect is ideal. In real applications, we typically using the quasi-isotropic laminates, such that we have many different angles, but to approximate the isotropic behavior, quasi-isotropic behavior. Okay, we want to have A11 equal to A22, and A11 minus A12 equal to 2 times A33, A13 equal to A23 equal to 0. Such things is coming directly from the quasi-isotropic laminates, as shown here. So how do we use these equations? For given laminates, we can calculate the ABD matrix. And then for set of applied stress resultants N and M, we can calculate the epsilon 0 and kappa. And then we calculate strain at any point Z through the thickness using the relation here. Then we can determine the laminar stress using the equation shown here. And the laminar analysis program, actually, if we can develop that, we can greatly simplify the process. You see, that's how we actually, for laminates, if you are having many layer laminate, eventually you want to find out their stress, right? And that is how we do that, step by step. This is the applied stress, this is the ABD matrix, this is the strain, and then from that we can work out the stress, right? So we will use another lecture to explain these example problems here. I'll leave here for you to solve the questions. Thank you.